Hey, welcome back. For a moment there, I thought I was going to be by myself here. You fixed. Hope everyone had a good break. It's a reminder that exam number 3 due today, so don't forget about it. And that's over chapters 7, 8, and 9. All right, any questions about those chapters? If not, I'll jump right into chapter 10. Any questions? Yes, go ahead. I can barely hear you.
Oh, sorry.
Yeah.
How can you tell whether an acid is a really strong acid or a weak acid?
Okay. Well, if you recall, we gave you a list of the strong acids like hydrochloric acid, HCN, HCl, HNO3, nitric acid, and sulfuric acid. Those are the main 3 strong acids that you're going to be working with. The other acids that we gave, carbonic acid, hydrofluoric acid, those are weak. And the only way really at this point, as far as Chem 30 was concerned, is basically just memorize the acids that we gave you with respect to which ones are strong and which ones are weak.
Thank you.
Yeah, no problem. And that's just the tip of the iceberg of the acids. There's other things we can do. If you go on to take Chem 150, 151, we have what's called the pKa value that you can look at that acid by its value and determine whether it is a strong or weak based on their value. But that's beyond the scope of Chem 130. So for right now, just look at the list I gave you. And those are the ones we're going to stick with. We won't throw you anything, throw a curve in you and give you anything out the window or unusual. Okay. All right. Any other questions? Okay. Well, let us continue then with chapter. Let me share the chapter 10, which deals with chemical reactions, okay? And the types of chemical reactions that we'll work with. Now, keep in mind, of all the chemistry that's out there, there are only 6 types of chemical reactions that we're going to deal with. 6 types. 2 of which one of which we talked about, and that is when we talked about the acid-base chapter, okay? The reaction of an acid and the base, it's a neutralization reaction. It neutralizes to give us water. That is one type of reaction. Another one that I mentioned is a combustion reaction. A combustion reaction is basically anything that burns. Now, we're going to be very specific about what is burning, what we are burning, and that we're going to be talking about what we call hydrocarbons. And those are organic compounds that we can identify as hydrocarbons because they're made up of nothing but carbon and hydrogen. Examples will be some that you're familiar with. If you did some cook-up this past weekend, you had a propane tank and you were cooking out, that propane, that is a hydrocarbon. That is just carbon and hydrogen. That is what makes up a hydrocarbon. Another one, if you got a lighter, butane, that's another example of a hydrocarbon. Now, with respect to that combustion, for anything to burn, we need oxygen. So in that case, a combustion reaction will consist of a hydrocarbon, oxygen, and the only 2 products you get are water and carbon dioxide. We'll have more to say about that. Okay, so, and then we're going to get into other types of reaction specific. But an important part about this whole thing about chemical reactions, we have to discuss what is called, which you may be familiar with, is the law of conservation of matter. Basically stating that matter is neither created nor destroyed. we're just moving things around, okay? We if we start off with an X amount of carbon atoms in the beginning, let's say we've got 10 carbon atoms in the beginning of a reaction, and those 10 carbon atoms could be made up of, it could be anything but 2 reactants. When we're done with that reaction, we're going to end up with 10 carbon atoms. Okay, and that's basically what the conservation of matter is telling you, which is together with the conservation of energy. But we'll just talk about the conservation of matter. Another way to say it this way is that if I have a total mass of reactants, okay, after the reaction is done, okay, so let's say I start off with 10 grams of, A plus B, total 10 grams. So maybe I got 5 grams of A, 5 grams of B. When the reaction is complete, maybe I make C plus D. At the end of the day, I should end up with maybe 7 grams of C and maybe 3 grams of D, okay? So the point being that if I start off with the total mass of reactants, when I'm done with the reaction, I'm going to end up with the same amount of material. During the time that we can be on face-to-face, I would do an experiment to show you and to demonstrate the conservation of matter. And it was a very, very simple experiment, okay? I would take, and let me do a drawing of it. I would take a flask, an Erlenmeyer flask, okay? And in there, I would put in some, what we call acetic acid, AKA vinegar. Acetic acid, very weak acid, by the way, okay? And then I would get a balloon, and I would put a balloon and fill it up with, in there with some sodium bicarb. By sodium bicarb or sodium carbonate. Okay, and so we have a base, we have an acid, and we're going to end up have an acid-base reaction. Okay, so I would put the balloon on the side, and then the whole thing I would put on a balance and weigh it. And it would weigh, I don't know, say 50 grams. Okay, then I would take that balloon and I would lift the balloon up so that that powder of sodium bicarb that was in the balloon on the side now falls into the container, which then causes a reaction. And one of the products in this particular reaction is carbon dioxide. And so when I let it run for a period of time, that balloon, here's the beaker again, bubble up, and then the balloon will fill up with the carbon dioxide. But my balance would still weigh roughly 50 grams. Now, obviously, it didn't weigh exactly 50 grams because the connection here, not 100%. Some gas does go away, but if we were doing under very strict conditions and everything was sealed up and everything, it would be 100% 50 grams. But it demonstrated that conservation matter. And what's happened is the vinegar now is totally changed to something else. Actually, it's made sodium acetate and carbon dioxide as the products. Okay, that carbon that used to be in the form of sodium bicarb now is in the form of carbon dioxide. And its total weight plus all the material in here would still end up to be a total of 50 grams. Okay, and that was a nice demonstration to demonstrate the conservation of matter. Okay, so as I stated earlier here, that if I start off with an X amount of carbon atoms or any atoms, regardless of what it is, that when I'm done with the reaction, I'm going to have the same number of carbon atoms. They may not be in the same form, but there's still carbon. Remember, carbon still has the carbon's element number 6 protons. If it's in the form of sodium bicarb or in the form of carbon dioxide, it is still carbon. It still has 6 protons, okay? It's just put together a little bit different than it started off as. We have to account for this because what we need is a balanced chemical reaction, okay? Balance, meaning that if I have 254 carbon atoms as a reactant, I'm going to end up with 254 carbon atoms in the product. And we have to put coefficients in the products that we create such that we make sure that we have a balanced chemical reaction. All right, so we're going to talk about how do we balance chemical reactions. Some of these reactions are very small and simple. And the 6 types that we're going to talk about, some of them it's a matter of trial and error, unfortunately. It's a matter, I put a 2 here that balances one set of atoms, but then it displaces another set of atoms. So I go to the product side and put maybe a 3 someplace to balance that out. And I go back and forth. And that's what we mean by balancing. We end up with a coefficient, maybe put in the product side, and then that changes the amount of maybe another atom. So we go back to the reactant side and we put in a coefficient there and we go back and forth, such that after we're done, there's sufficient number of atoms of whatever atoms are involved in the reaction, okay? So we first always write the chemical reaction, making sure the chemical formulas are correct. And so sometimes you're given a reaction in words. You have to take those words and convert them into chemical formulas, okay? And when we're dealing with ionic compounds, what we do first is we first write those compounds or these elements in ionic form. And we do that because we want to make sure that we put them together in the correct ratio, okay? All right, and then we add enough cations and anions so such that the overall charge of everybody is 0. Then once we write the formulas for reactants and products, then we start playing with the coefficients such that everybody's balanced. And like I said, some of these reactions, it's a matter of trial and error. However, some other reactions, we have a very specific way to assist you, to help you balance the chemical reactions, okay? All right, so now remember, once we write the formulas and we have, H2O, for example, okay? Once we write the formula and let's say we're dealing with water, once that subscript is set, it's set in stone. We don't change that, okay? But the coefficient up here, we can change whatever we need. If we need 3, or we need 10 atoms of or molecules of water, or we need 1,000, we can change that coefficient as many times as we need, but not the subscripts, okay? I know sometimes people will say, oh, well, I need 2 molecules of water. Okay, so you write 2 in front, the coefficient in front of 2 of H2O. What I've seen is some people would take the numbers here and write H4O2, but that is not water, okay? That is not water. I don't know what that is, but it's definitely not water. So we don't play with the subscripts. We play with the coefficients all we want until we got everybody balanced. Okay, for example, here's a reaction that could be given in words, okay? But I'm giving you, it's given in formula. It could say something like this. Hydrogen in the presence of oxygen reacts to form water, okay? That could be given the sense. So you would take hydrogen, realizing that hydrogen gas, I would say hydrogen gas, is diatomic, so I would put H2, okay? In the presence of oxygen, which is another way of saying plus, okay, or reacts with, okay, other words, in that manner, reacts with in the presence of oxygen is a signal for plus oxygen gas, which we know is diatomic, okay, reacts to give you water. And so we will write that reaction as follows. Now we have to balance everybody, because if you look at what I just wrote, we have 2 hydrogens on the reactant side and 2 hydrogens on the product side. So hydrogens are balanced. We're happy, okay? If we look at oxygens, we have 2 oxygens on the reactant side, but only 1 oxygen on the product side. So we're not balanced. So we have to put a number, a coefficient such that we balance the oxygens. We can start with that. So if I put a 2 in front of H2O, that changes the oxygens to 2, but it also changes my hydrogens now to 4, okay? On the product side. Then on the reactive sides, oxygen's still set at 2, but hydrogens are set at 2 as a reactant. We now have 4, so we simply put a 2 in front of hydrogen gas. Now that becomes 4 hydrogens on the reactant side, 2 oxygens on the reactant side, and that also balances out with 4 hydrogens on the product side and 2 hydrogens on the product side, 2 oxygens, excuse me, okay? So you can see, hopefully, that now we have a balanced chemical reaction. And another way to show it is, using the space field models here. You can see here that we have 4 hydrogens, okay? And they happen to be two of them, 2 molecules of hydrogen have to be in the form of diatomic hydrogen, right? And then we got 2 oxygens. And then when the reaction proceeds, we now have two molecules of water, okay? And here's our 2 oxygens in white and our 4 hydrogens in gray. And so it's still hydrogen to begin with, either as a reactant or as a product, but it's in a different form. Okay, the same is true for oxygen. Oxygen went from diatomic oxygen to a molecule of oxygen. And so we're balanced. Now, what this does is a couple of things. We now have a ratio. Okay, you might say ratio, that sounds familiar, right? Remember when we were doing conversion factors? Remember way back when we were in the beginning chapters, we had, 1 inch was equal to 2.54 centimeters. And remember we talked about, I can write that ratio in 2 ways, with centimeters on top or inch on top, okay? Remember that? Okay, and I said, this is a method we need to learn here, because when we're going to start doing chemical reaction calculations, we're going to use this ratio system to help us to go from reactant to product or from product to reactant. And here we are, because now, once we have balanced our chemical reaction, we have these stoichiometric numbers in front that we can write as ratios. And so the ratio between hydrogen and oxygen is understood to be a 1, it's a 2 to 1. So we can say that 2 hydrogens over 1 oxygen is 1 ratio, or we can write that as 1 oxygen on top with 2 hydrogens in the bottom, okay? We have 2 conversion factors, and that's between the 2 reactants. We can also see that we have a ratio between the hydrogen and the water, which is 2 hydrogens of 2 molecules of hydrogen and 2 molecules of water. So again, we can write that with water in the numerator or water in the denominator. And then we got the relationship with oxygen and water, which is a 1 to 2. Now we can do calculations, because remember when we did the calculations of the inch, the units, I always stated, remember, the units we want to end up with at the end will end up being the numerator. And so we have a problem that says, well, if I have 10 molecules of oxygen, how many molecules of hydrogen do I need? Well, I'm going to use the left one, because if I have 10 oxygens and I'm going to multiply it by this factor, guess what? My oxygens cancel, even with hydrogen. So I need 20 molecules of hydrogen for every 10 molecules of oxygen, because it's a 2-to-1 ratio. Okay. All right. So keep that in mind, why it's important, because you could be in a situation that you could be asked, all right, I need to make 100 grams of water in this reaction. How many grams of hydrogen do I need? You see? That could be the question. And that this reaction is true whether you do it in the lab in, say, gram scale, or you're doing it in an industrial plant where you're making tons of this material. Okay, that chemical, that relationship between hydrogen and oxygen is still the same, regardless of the magnitude, the quantity of material you're using. All right, so balancing chemical reactions are very important. So let's take a look at this. And again, it could be written in words and say nitrogen in the presence of hydrogen reacts to produce NH3, aka ammonia. Okay, ammonia. All right, so we look at this and we can attack this problem a couple ways. This is one type of reaction that, they're simple reactions, and we can do a trial and error kind of thing so we can get the atoms balanced. So let's find out where we at first, okay? We have 2 nitrogens on the reactant side and 2 hydrogens total on the reactant side. And we have 1 nitrogen on the product side and 3 hydrogens on the product side. So you can see right away that nobody's balanced here, okay? Nobody's balanced. All right, so you can attack this problem a couple of ways, all right? First thing I notice is that I have a relationship here. When I look at hydrogens and I just look at them by themselves, I got 2 on the left and 3 on the right as products, right? Guess what? Remember that when we're putting formulas together, like calcium and nitride, and we had to find a common number, remember that? And we ended up with CH3N2 as a formula, and we had to find a common number. Well, you got a similar situation here, because I got a 2 and a 3. The common number here obviously will be a 3. So if I put 6, excuse me, if I put a 3 in front of hydrogen gas and I put a 2 in front of ammonia, what does that do? Well, that kicks up my hydrogen from 2 in the reactant side to 6, okay? And on the product side, it went from 3 to 6. So my hydrogens are now happy. Because I put a 2 in front, my nitrogens went up with a 2. And guess what? By default, that balances out my nitrogens, okay? All right, so I end up with, let me clear this up, with the following. So I'm putting the 2 there, and then the 3 that balances out my hydrogens, all right? And by default, my nitrogens get balanced. Now, as you're balancing these chemical reactions, be aware and take a look at the where we call the relationship between the reactants and the products. Between nitrogen and hydrogen, it's a 1 to 3. Okay, it's understood to be a 1 there. So think about this for a moment. For this reaction to occur, I need 1 molecule of nitrogen and I need 3 molecules of diatomic hydrogen, 3. And when it's done, I will have 2 molecules of ammonia. Okay. So you can see I got 6 hydrogens total here and 6 over here, 6 hydrogens. My nitrogens are balanced. All right. So also check that. That's what I did. I wrote them out longhand until you become confident in just reading the equation. But in the meantime, put them out molecule-wise so you can see that everybody's balanced. Then the other thing I notice is I look at the relationship between reactants. There's a 1 there. So that means that I have a ratio, if I need to do a reaction calculation, of 1 nitrogen, excuse me, I wrote ammonia, I got ammonia in the brain here. 1 nitrogen per 3 hydrogens, or I can write it by inverting it, okay? That's one relation, the relationship between reactants. And keep in mind, the other relationship is between the nitrogen and ammonia, and between hydrogen and ammonia. Take a look at that one, hydrogen and ammonia. That means that there's 2 ammonia per 3 hydrogens. I can write it in that form, or I just simply invert it. Okay. All right. And depending on the problem, you know, they might ask you, all right, if I need 30 ammonias. Question is, how many hydrogens do I need? All right, I need 30 ammonias. How many hydrogens? So our relationship that we need to look at is simply between ammonia and hydrogen, which means this one of these 2 right here. Okay. Question is which one? Well, look at the question. I have 3 ammonia. How many hydrogens I need? So the hydrogen is what I'm looking for. So I would use the one on the right. So I write down what I'm given, 30 ammonia. Okay. I'm going to use the one on the right. And look at my units. My units of ammonia cancel, leaving me with hydrogen units, which is what I'm looking for. Okay. And so that means I have 15, that's 15, 45 hydrogens. If I start off with 30 ammonia, I need 45 hydrogens, okay? 45, because that ratio between the hydrogen and ammonia is a 3:2. Okay. All right. Now notice we're just been talking about molecules, but the next step is that we can't talk about I need 10 molecules, because it's not like you can go to the lab and measure out 10 molecules, but you can go up to the lab and measure grams. Okay, so we're going to talk about in the next few chapters how to go from molecules to grams. Okay, all right, so let's take a look at this one here. This could be stated as hydrogen in the presence of bromine. Okay, reacts to give you hydrogen bromide. Hydrogen bromide, because it's a gas. Normally, those aqueous system can be called hydrobromic acid, but called hydrogen bromide right now. So we could do a couple of things. Well, trial and error again. So we can see we have 2 hydrogens. So I do my little grocery list, if you will, keeping track of how many atoms I have of each. I got 2 hydrogens, 2 bromides. I got 1 hydrogen on the product side and 1 bromide on the product side, right? So obviously everybody is not balanced, but I could put a 2 in front of HBr. And what that does, it gives me 2 hydrogens and it gives me 2 bromides. Okay. Now that by default just balance me out, because my bromides and the product and reactant side are 2, and my hydrogens are 2. So they're balanced. I'm good to go. Okay. And look at the relationship again as we proceed. We got 1 hydrogen for every bromine, excuse me, to produce 2 HBRs. We have a whole chapter in this called stoichiometric relationship. All right, here we have carbon monoxide in the presence of oxygen reacts to give you carbon dioxide. Okay, so we can put a 2 in front of carbon dioxide. What that does is, oh, let me back it up a little bit. Let's go stepwise so we're comfortable. We have 1 carbon over here, and we have a total of 3 oxygens on the reactant side. 1 in carbon monoxide and 2 is oxygen. On the product side, we have 1 carbon and we have 2 oxygens. Okay, so one way to do this is if we put a 2 in front of carbon dioxide, what that does is increase my carbon, so I change that to 2, and increase my oxygen to 4. Okay, so what I can do, my carbons, if I put a carbon, since I got 2 carbons now, I can go in and go back to the reactant side and put a 2 here in front of carbon monoxide. What that does is that balances out my carbons now. Now my oxygens go to 4 because I got 2 in the form of carbon monoxide and 2 oxygens in the form of oxygen gas. And guess what? We are balanced. Okay. Balanced chemical reaction here. All right. So anyway, as I stated, we gave you the formulas here, but again, you could be getting questions in the sentence, and you need to convert this sentence into a chemical reaction. Right. In doing this, don't forget to include the physical states of solid, liquid, gas. Okay. Aqueous solution, AQ, it's the material dissolved. And remember, if you're working with the elements, which ones are solids, which ones are gases, which ones are liquids. Okay. 118 elements, only 2 of them are liquids. But a dozen of them are gases, and that means everybody else is a liquid. Okay, don't forget which ones are diatomic, have no fear of ice cold beverage. And then don't forget that the subscripts tells us how many atoms there are in a molecule. Coefficients tells us how many molecules you're dealing with. All right, let's take this reaction. So you have sodium reacts with chlorine to produce solid sodium chloride. Okay? Solid sodium chloride. Well, we have sodium, and that all they say was just sodium, so we're talking about the element of sodium, which is a solid. Okay. And then the keywords reacts with, which is indication to tell you it's a plus symbol. Sodium reacts with chlorine. Remember that chlorine is a gas and it's diatomic. Okay. To produce is a flag to tell you it's our reaction arrow. To produce or gives or produces, any of those type of words, that's our cue to say that's our reaction arrow. And now we have solid, so they give you the physical state, so we're dealing with solid material. And then they say sodium chloride. So sodium chloride should indicate to you we have an ionic compound, okay? Because we have a metal and a non-metal combination. But before we put them together, write the formula, write them in the ionic form first. We know that sodium in ionic form is a +1. How do we know that? Because from the periodic table, sodium is in group 1. It has 1 valence electron. It is a metal being a metal, it would lose electrons. Metals lose electrons, therefore it will have a plus sign. Chloride, okay, is in group 7. It's a group 7 element. And the term "ide" versus "ein" to indicate to you you're dealing with the ion, okay? It is in group 7, and that means that chlorine will gain an electron to produce chloride because it's a non-metal. So that's the ionic form of sodium ion and the chloride ion. Now we put them together and we can see it's a straightforward 1-to-1, okay? And so the formula would be simply NaCl, okay? And that's why it's important that we put them in ionic form first, so to make sure that we are able to write the correct formula, okay? All right, now, the next matter is balancing and solid, excuse me, because it's solid, it's telling us it's right there. They told us it was solid. So we got the formula written, but it's not balanced. We got 1 sodium on each side. Sodium's happy. Chloride, the Cls, where we got 2 on the left, 1 on the right. Well, what if we put a 2 in front of sodium chloride? Well, that takes care of the chlorides, the Cls. But it now causes the sodiums to increase, no problem. We put a 2 in front of sodium, and now we can see that everybody is balanced. So 1 sodium, 1 chlorine produces 2 sodium chloride, okay? And then we clear this up a little bit. Okay, this is what we just did. And then don't forget to add the states, okay? And we know that chlorine is diatomic, obviously, so it can't be, formula-wise, it cannot be sodium Cl2, because that would suggest that sodium has a +2, which then would suggest that sodium will be a group 2A element, when it's not the case, okay? Sodium is a group 1A, Roman numeral 1A element, has 1 valence electron. That's a fact. This is a fascinating reaction, actually, when we think about it, because sodium is a very, very reactive metal. It's so reactive that we have to store it under mineral oil. Any aqueous comes close in contact with water, it reacts violently. Okay, you can YouTube sodium. Sodium people have taken made videos of taking chunks of sodium and tossing them in the river, and they can see how that thing is bubbling up. I used to also do, when we had live class, a demonstration on the sodium and how reactive it is with water, but I can't do it here. So anyway, very reactive metal. And then chlorine is a poisonous gas. Wouldn't breathe it in very well. And yet, when they come together to form a product, they create sodium chloride, which you can put on your French fries. Okay, perfectly safe, unless you got high blood pressure. Okay, and the thing that happened here is that there is a transfer of 1 tiny electron from the sodium to the chlorine. Actually, there's a total of 2 of them, but an electron transfer occurs. 2 electrons come from 2 atoms of sodium, 1 molecule of chlorine gas to produce 2 sodium chlorides. So there's a total of 2 electrons, and that exchange of electrons produce products that are drastically different as far as the physical properties. All right, so let's try another one. In this scenario, they're asking you to aluminum. Aluminum reacts with, so we can write aluminum. We know that we're talking with good old L. And aluminum, element aluminum is a solid, okay? Reacts with is a flag for plus, reacts with bromine. As chlorine, bromine is diatomic, okay? Plus, that's also a liquid, one of two liquids. Anybody know what the other liquid is as far as the elements are concerned? The metal, mercury. Okay, so we got bromine and aluminum reacting to produce solid aluminum bromide. Again, as the case with sodium chloride, we have an ionic compound. So we have to write the ions first. Aluminum is a metal, and therefore it's a group 3A, and it will lose 3 electrons to end up with a +3 charge or oxidation number. Bromide, like the case in chloride, it's group 7, so it would end up with a -1 charge because it will gain 1 electron. It's a non-metal. And so here we have the cation and the anion, and we need to use 3 bromides for every aluminum ion. So the formula is AlBr3 in its solid. Okay. Again, I cannot overemphasize to write the ions, the ionic compounds in ionic form first before you put them together. I can't tell you numerous times for aluminum bromide, I've seen formulas like this, okay, which is incorrect. I've also seen aluminum Br2, which is also incorrect because they thought that aluminum was a group 2 element. It's a group 3, +3. Okay, now we have the chemical reaction, and now we got to balance it. Okay, notice something. We got a 2 to 3 relationship like we had earlier. So we can simply find a common number, which in this case is 6. So we put a 3 in front of bromine and a 2 in front of aluminum bromide. That balances our bromides or Brs, but that kicks up the aluminum, so we can simply go to aluminum, put a 2 in front of it. Okay, that's how balancing works. You start off, you could start off in reactant side or the product side, makes no difference. You put a number down, the coefficient. Normally what that does, that sends you back to the other side. You put a coefficient there, and sometimes that sends you back to where you were. So you go back and forth with the coefficient such that so many times, whatever it takes until such time you're balanced. Now, a note about balancing. It is feasible that when going back and forth that you end up with all these numbers that are double. So for example, you might end up with 4, 6, and 4 as the coefficients. Now, technically, it is balanced, right? It is. If you think about it, got 4 aluminums on each side. You know, I got 12 bromides on each side, Brs. If I use the coefficients 4, 6, and 4. When you're done balancing, the last thing you should do is check to make sure that the coefficients you have been reduced to, quote, the lowest terms, just like the mathematics, okay? So if you end up with 4, 6, and 4 as the coefficients, note that they are divisible by 3, and you can reduce everybody down to 2, 3, and 2. Okay, so bring it down to the lowest terms. All right. Clear it and proceed here. So we have write the formulas, which we did, and then we added the states. Okay, and then we start to balance it. We put a 2 in front of aluminum bromide, a 3 on front of the bromine, and then a 2 with aluminum. Okay, and so now we have a balanced chemical equation. When you do that, note the relationship between aluminum and bromine. Okay, it's a 2 to 3 relationship. Note the relationship between aluminum and the product aluminum bromide is a 2-to-2 or a 1-to-1 relationship. And the relationship between bromine and the product, okay, which is a 3-to-2 relationship. Okay, so in this case, you have a total of 2, 4, 6 coefficient ratios that you can write for these 3 different relationships. Okay, let's. Okay. Write the proper formulas, and then obviously you don't change the subscripts, and we add the coefficients. It is these coefficients that I stated that you can write and we can utilize to do any calculations. So aluminum to bromine, that relationship is 2-to-3, so we can write it either with aluminum in the numerator or aluminum in the denominator, okay? And we can do any type of calculation that people throw at anybody, throws at you. If you don't have a balanced chemical equation, obviously your stoichiometric relationship would be incorrect and your calculations would be off. All right, here we have another one. It's saying here, write the reaction of phosphorus reacting with oxygen to make diphosphorus pentoxide. Okay, well, let's break it down. Okay, so write the reaction of phosphorus. So that would be P, okay, which is solid. Reacting with is indication for a plus symbol, oxygen, okay? Oxygen is diatomic and it's a gas. Okay. Then we're making a covalent compound here, right? Why? Because we got phosphorus and oxide, 2 nonmetals. So we have a covalent compound. So write the formula. And my suggestion, as in the case of ionic compounds, where I said to write the ions first. Obviously, we don't have ions here for covalent compounds, but write the base formula first, okay? We have phosphorus and oxide, so it's P and O. That is our base formula. Then we look at the prefixes. We got di, meaning we got 2 phosphorus, and penta, meaning we got 5, okay, oxides. And they are it's solid, so that's our formula, P2O5 solid, okay? All right, so now we're done with that, we get a balance. So let's look at this carefully. We got 1 phosphorus over here, we got 2 oxygens on the reactant side, 2 phosphorus on the product side, and 5 oxygens on the product side. So obviously nobody is balanced. So we got to balance. My suggestion would be, hey, look at this relationship. Earlier we had a 2-to-3 relationship, in this case oxygen, but here it's a 2-to-5. So we can tap into that method we did earlier. We find a common value, right? So if we put a 5 in front of oxygen, that gives us 10 oxygens on the reactant side. And if we put a 2 in diphosphorus pentoxide, that gives us 10 oxygens. That balances out the oxygens. We're good with the oxygens, okay? But in the process of putting the 2 here, that kicks up the phosphorus to 4, okay? No big deal. We go back to the product side, the reactant side, and we can simply put a 4 in front of phosphorus. And now we are balanced. We got 4 phosphorus on both sides. We got 10 oxygens on both sides, okay? So everybody is happy, all right? And we're balanced. Mother Nature is happy. So then, all right, there's the formula, the physical states, and now we're balanced. Note the relationship. We got 4 phosphorus over 5 oxygens. Or 5 oxygens over 4 phosphorus. So you might be asked the question, I don't know, let's say if I have 10 phosphorus, how many oxygens do I need? Okay, so what am I looking for? I'm looking for oxygens, and I'm only dealing with the 2 reactants. So the relationship I'm looking for is the 5 oxygens to 4 phosphorus. Furthermore, since oxygen is what I'm looking for, I'm going to use the one on the right. Okay, so I write down, just like we did the conversion factors, write down what we know, what we have. We are looking for amount of oxygen, so that means we have a conversion factor in here. We're going to use the one on the right, where we got 5 O2s and 4 phosphorus. And that comes at 5 to 4 comes from the balanced chemical equation. Okay. All right. So with that in mind, now you simply just plug in the numbers, and you have your value, right? So we got was it 10? Oops, 5, 4. So 12 and a half. Check my math. I got 12 and a half O2s. About 4 and 5 oxygens are needed if I start off with 10 phosphorus. All right. Any questions so far? Okay, now this one definitely looks complicated, but you know what? As any complicated issue that you may come across, when you break it down into its pieces, you're going to find out it's not as complicated as you might first think. Okay, and so this actually is an example of the third type of reaction. Okay, we'll explain that for a second, because we just talked about acid-base reactions, and then we talked about combustion reaction, and this is the third type. We're going to combine all of them here pretty soon, but we're kind of introducing them a little bit at a time. Here, it's asking you to write and balance this aqueous reaction. Okay, nickel 3 sulfate plus lead 2 nitrate produces nickel 3 nitrate and solid 2 sulfate. Okay. All right. As anything, break it down into the pieces. And notice here, in both cases, everybody here is an ionic compound, right? So what do? We write the ions first. Let's write the ions first of all these compounds, so we can make sure we put them together correctly. So let's take the first one. It says nickel 3 sulfate. Well, nickel 3, okay, I'm going to make this red. Nickel 3 tells you that you're using the +3 ion. And the sulfate, well, hopefully by now you can recognize the ATE, which should tell you, go to the polyatomic ion table on the periodic table, okay? If it was sulfide, IDE, then you know it's just sulfur by itself. But the ATE means I got sulfur plus oxygen bonded with it, okay? How many oxygens? You may not know what it is, but the ATE should direct you to the periodic table. And if you look that up, you'll see that it has this formula, SO4 -2, okay? All right, so that is let me change the color a little bit. That is the ion for the first one. Then they say plus. Well, that is a flag for the plus symbol, obviously, okay? And the next one, lead 2. Well, lead 2 is Pb +2. Remember Roman numerals represent the oxidation number of the metal. Lead 2 plus, we're working with nitrate, so it's NO3 -1. Nitrate. Not nitride, which would be nitrogen by itself, but the ATE, as in the case with the ATE of sulfate, should send you to the polyatomic ion table, and that is the formula right there. All right. Now, so we got to write them all in ions. Let's do one more. It says produces, that's a flag for the reaction arrow. Produces, okay, nickel 3, so we're still dealing with nickel, Roman number 3, so that's a +3, and the nitrate, which is a NO3 -1, and the and symbol is indication of, choose a different color here, and tells you plus solid lead 2 sulfate. So we have lead 2, which is Pb +2 plus SO4 -2. Okay, and it's a solid when we put them together properly. So right now what we did was put everybody in ionic form. By doing that, then we can put everybody back together now with the correct number of ions for each other, and then continue. All right, so here we have the nickel +3 and the sulfate -2. Okay, we have a disparity here of a +3 and a -2. So we can use that little trick of finding a common number, which is 6 again. And so we can go through the exercise and we end up with the following formula. Okay, 2 nickels and 3 sulfates. All right, the lead, okay, here, okay, because we need 3 there and 2 there. Lead is a +2, nitrate's a -1, so all we need is 2 nitrates, so we can use the parentheses because we need 2 nitrates, and that's done. Now everybody's an aqueous solution, so we got AQ and AQ. Okay. Now let's put the nickel 3 nitrate together. You can see the nitrates are -1. We need 3 for every nickel +3. So it becomes Ni parentheses NO3. Okay, 3. Okay. Also aqueous. Then plus lead sulfate. Well, I got a +2 and a -2. Right? So they can come together as a 1-to-1 because it's a solid. Okay. All right. So now we've written the chemical reactions, the formulas for what was given to us in words. And we did that first by putting everybody in ionic form. That's important. Okay. Hold on 1 second. Give me 1 second. Right. All right. So let's go back. So here we got the formulas. Now what we got to do is we got to balance it. Now this type of reaction is what we call a single replacement reaction. Notice what happened here. is when we look at the reactants, we start off with nickel sulfate and lead nitrate. What's happened is the partners, the anions and the cations, have exchanged partners. So the nickel now got together with the nitrates to form nickel nitrate, and the lead got together with the sulfate to form lead sulfate. Now, based on the solubility rules, we see, you can look it up, but you'll see that lead sulfate is insoluble in an aqueous system. And so we put a solid, whereas nickel nitrate and all the other, the nickel sulfate and lead nitrates are all soluble. They're all in solution. The only one that is not soluble is the lead sulfate. In fact, the two, if we had two beakers of the reactants, would be clear solutions. And if we put them together, mix them, you get a powder, okay? And it will precipitate because the lead sulfate is insoluble. So that would be a positive reaction. And when both of the products for these type of reactions, if both of the products were soluble based on the solubility rules, then we get no reaction. But one of the new products is insoluble, and so this would be a positive reaction. So this is what we call a single replacement reaction. And we'll talk more at length about this one here in a bit. All right, so now we have the formulas. We got to balance it. Now, when it comes to these type of reactions, yes, you can go there and count every sulfur, every oxygen, every nitrogen, and so on, which can be very complicated, and keeping track of all this thing. Our suggestion is this: follow the polyatomic ions, okay? Follow the polyatomic ions, and in doing that, that will aid you in balancing these reactions. And so remember, we talked about the polyatomic ions. We keep those as a unit. We don't separate them when they have their own specific name. The sulfate has their own name, the nitrate, okay? And we can use that property to follow them and balance them out properly. All right, for example, if we start off where we began in the beginning, let me change my color a little bit here. We had 3 nitrates, okay? In the beginning, 3 nitrates, all right? Well, on the product side, we have only, excuse me, I said I got nitrates in the head. I meant sulfates. We got 3 sulfates on the reactant side. On the product side, we only have 1, okay? So what if we put a 3 in front of lead sulfate? That will balance out the sulfates, okay? So the sulfates should be okay. They're all taken care of. I got 3 there, and I'm gonna have 3 here as lead sulfate. Well, what that does is that kicks up my lead count, okay, to 3. All right, no problem. So we go back to the reactant side and notice that there's only 1 lead on the reactant side. So what happens if we put a 3 there? If we put a 3 in front of lead nitrate, that balances out the lead nitrate, no problem. But there are 2 nitrates in lead nitrate, and with that 3, that makes it 6 nitrates, okay? No problem. Go back to the product side. Look at where the nitrates are. There's 3 of them here. Put a 2 there in front of nickel nitrate. That kicks up the nitrates to be 6 nitrates in both sides. My nickels now get kicked up to 2. All right, so we go back to the reactant side. By default, nickel's fine. I got 2 nickels there. So let's go back and rehash. I got 2 nickels. Nickels are good on both sides, okay? Sulfates, I got 3 sulfates on the reactant side and 3 on the product side. So the sulfates are good, okay? I got 3 leads on the reactant side and I got 3 leads on the product side. So they're good. The nitrates, I say, were good because we got 6 on the left side, 6 on the right side. So the nitrates are good. And what's left? The nickels. We got 2 nickels on the product side and 2 nickels on the reactant side. And lo and behold, everybody is now balanced, okay? Now balanced. To rehash, for these type of reactions, especially when they're all ionic compounds, like it's written up there, break them down into the ion first so you can make sure you can write the correct formula, okay? Then at that point, balance it out. And our suggestion is this: to balance these type of reactions where you have a lot of polyatomic ions, follow the polyatomic ions. All the other partners will fall in place as far as the cations are concerned. So follow the anions. All right, so this should end up with that, and that relationship is 1 nickel sulfate ratio to 3 lead nitrates. Okay, so you really have a lot of relationships here. You got this relationship between the two reactants. Okay, that is 2 ratios that you can write. Okay, now you have the relationship between the nickel sulfate, and the nickel nitrate. Okay, so now you got 4 ratios that you can make. Then the nickel sulfate and the product lead sulfate. And there's 2 more ratios. So now you got a total of 6 ratios that you can write up. Then you have the lead nitrate and the nickel nitrate relationship, which is in this case is a 3:2. So that's 2 more ratios you can write. And then the lead nitrate to the lead sulfate, which guess what? Gives you 2 more. So you got 10 ratios that you can write. And then finally, the relationship between the nickel nitrate and the lead sulfate, and that's 2 more. So you have a total in this chemical reaction here, you have a total of 12 ratios that you can write that relate reactants to reactants, or reactants to products, or products to each other, okay? 12 ratios that you can use to do any type of calculation that can be thrown at you, okay? All right, so let's talk about the 6 types of reactions and in general, generic terms, okay? So we're using the letters A, B, and maybe my C in there. Okay, a combination reaction. Normally what's happening is you're getting 2 elements that come together, okay? 2 elements that come together to create a compound. So A is an element, B is an element, they come together to form AB, which is a compound by definition, 2 different elements, okay? A and B are not real elements, I'm just using those as examples. So they come together, it's a combination, they combine. What can happen is a decomposition. So you can have a compound, begin with a compound, and break it apart. And so you then have broken it apart into its elements. And so, for example, a classic example of both of these would be hydrogen. Let me change this a little bit. Yeah, a good example would be hydrogen gas plus oxygen coming together to form a compound, good old-fashioned water, okay? A lot of rockets use that as a fuel. In fact, you can see the big old flume of smoke coming out, which is seen as water vapor coming out. Okay, so that's 2 elements come together to form a compound. On the other way, you can take water and hit it with some electricity and break it down to hydrogen and oxygen, okay? Decomposition going the opposite, but it takes a lot more energy. The forward reaction, hydrogen and oxygen, is pretty spontaneous, but getting it back to the elements takes a little more energy. Okay. All right, a combustion reaction. Now here's what I spoke to you about earlier. We are going to work with hydrocarbons. And so in this example here, you see the general formula of CH okay, CXHY, where X and Y represent obviously coefficients, okay? But the main point is it consists of nothing but carbon and hydrogen in the molecule of the hydrocarbon. Now, to burn anything, the key ingredient for any combustion is oxygen. So oxygen is always a reactant, always involved in the reaction. So you might be asked, given the question, the combustion of butane, you're given the formula for butane. What is write the reaction of butane, a hydrocarbon? Well, you'll be given a formula, so that part's given, and you should recognize that it's combustion, so I need to have oxygen as a reactant. And second of all, the only two products, okay, for any combustion reaction of a hydrocarbon with respect to Chem 130 are as follows: carbon dioxide and water, okay? Yes, I know your fuel is a hydrocarbon. Yes, I know that you form carbon monoxide in the fuel you use to burn your fuel here in your vehicle. And that's the case because our inefficiency of our motors to burn the hydrocarbons effectively. Okay, so yes, there will be carbon monoxide coming out the back in the exhaust. But for our purposes in Chem 130, the only two products that you need to know you will get is carbon dioxide and water. Okay. All right. Now, and there is a specific process to balance these type of reactions. We're going to talk about that, how to balance combustion reactions. Okay, you go through a stair-step process. You balance the carbons first, then the oxygens, and then the carbons, hydrogens, and then the oxygens. I'll give you some examples of that when we get to it. Okay, combustion reaction. Acid base, we spoke in this chapter an acid and base. We have an acid, and that by definition is anything that produces a proton reacting with a compound that produces a hydroxide ion, which will be a ionic compound, right? M is a metal and OH. And the only product you get will be water and the corresponding salt, which is the metal, whatever metal that was, and the anion of the acid. Okay. All right. So all right, single replacement reaction. Well, what this does is this. What happens here, if you look at this, let's break this down. We have a metal in elemental form, okay? A is also a metal. We're talking about ionic compound here, AX. So it's also a metal, but it is in ionic form because it is combined with X. X could be some anion. What happens is the metal in elemental form displaces or replaces the metal in ionic form. So now your new product is MX, and you have generated the A back to element. A good example of this would be plating. When you plate, say copper, you start off with copper in ionic form in solution, and then you run it through a process, and that copper gets moved and converted back to elemental form, and you're able to plate whatever you're plating with the copper coating. Same thing with gold, same thing with any metal, chrome, good examples of that, okay? Now, what drives this process is as follows. On the periodic table, we have underneath, on the right-hand side here, right above the solubility rules, we have a table which is right in here. And that's called the activity series. We're going to learn how to use this activity series, but in a nutshell. But it's telling you here that lithium metal is a lot more reactive than gold. See how that goes? Lithium is more reactive than potassium, than barium, et cetera, et cetera, et cetera. All of these are relative to hydrogen gas, okay, H2 or water. And so depending on the position of the metal with respect to the activity series, that will determine whether a reaction will proceed or not, okay? And then the last one, I'm going to call it quits here. Sorry, I need to go over the time here, is an example of this is a double replacement reaction where the one we just did. The M here represents metal, and the 1 and 2 subscripts are just representing different metals, okay? Both ionic compound, both reactants in this case are soluble based on the solubility rules. And generally what happens, one, if there's a positive reaction, notice that the partners exchange. Metal 1 now becomes metal 1 with Y. Metal 2Y now becomes metal 2 with X. So they exchange the anions. And depending on the solubility rules on the periodic table, if one of these is insoluble, then you get a positive reaction. If both of the products are soluble, then you get no reaction, okay? No reaction. So those are the the 6 reaction types that we're going to work with. And we're going to do some specific examples. And we're going to talk about how to balance some of these. I already talked about the double replacement reaction to follow the polyatomic ions, okay? And then the single replacement, the single replacement combination decomposition, those are mostly kind of trial and error a little bit. The combustion, we have a step carbon, hydrogen, and oxygen to balance in that order. And then the acid base followed the proton and the hydroxide, okay? Anyway, we'll give you some, I'll talk about some specific examples and how to balance them and how to make these work. All right, so let's stop it here.